Assalamualaikum and a very good day to the assessors and everyone. Today, I am attending the 2021 9 IEEE Conference of System, Process and Control. I will be presenting my study regarding the assessment of various additives in Magnetorheological Elastomer for impact application. And it is prepared by me, Normi Dato Salwa binti Sobri, Diazul Zakri bin Baharudin, Nur Akmal binti Hanifah, Dr. Zulkifli bin Abdul Kadir, Associate Professor Dr. Hizbullah Huda, and Tech Dr. Vimal Rao Aparau. I will start my presentation with introduction. So what is the Magnetorheological Elastomer, which is MRE? MRE is a smart materials that can change its properties when the magnetic field is applied. From figure A, this is the common matrix of MRE, which contain carbonyl iron particle or CIP. So the carbonyl iron particle is scattered for the common MRE. But in figure B, when the magnetic field is applied, the carbonyl iron particle will be aligned. So in engineering application, MR materials are usually proposed as the stiffness and damping elements in piston and absorber within the vibration isolation systems due to their controllable magnetic properties. MREs have been progressively investigated because of particular benefits over MRF, which is magnetorheological fluid, such as non-precipitation of magnetic particles and no spillage of the liquid. So this is the uses of MRE in impact mitigation application. The first one is the tunable spring element, where the MRE is located between the coil. And the next one is the MRE bushing, where the MRE also located near to the wire coil due to the magnetic field. My research starts with the fabrication of the MRE. MRE has three main components, which are rubber, ferrous particle, and binder. And I will be adding the four types of additive, and the additive which is copper, zinc, ferrite, and aluminium. The additive is classified to two groups, which is magnetic and non-magnetic additive. Ferrite and zinc is the magnetic additive, while copper and aluminium is the non-magnetic additive. So the fabrication starts with the mixing process. All the components will be mixed into a container and will be manually mixing, and the mixture will be poured into a mold. After that, it will be cured for about 24 hours, and the cured MRE will be put into the MRE test device for the impact testing. So this is the materials and the variables. The materials that are used for the ferrous particle is the carbonyl iron particles or CIP for 60%, and the rubber that I use is the room temperature vulcanization silicone rubber or RTV silicone rubber, which is 30%. And the four types of the additives that I mentioned earlier is the 10% from the weight of the CIP, and the adhesive or hardener is 3% from the weight of the CIP. The next one is the variables for the drop impact test. So the impact energy is the 11 joule, and then the impact velocity is 2 meter per second. The falling height is the 204 millimeter, and the tub holder mass is 4.3 kg. Tub nominal mass is 1.2 kg, and the specimen support is 3 mm, and the varying current is 0 to 2 ampere with the 0.5 step. Moving on to the drop impact test setup. So this is the setup of the impact test, which include the PC setup, the DAQ, and also the drop impact test shown the MRE suspension system. This is the result. This is the fixed type additive with varied current. Based on the result, Forces increase when the input current increase, resulting in a higher pressure exerted on the MRE. The trend results were shown to trend consistently downward to settling mode when the increase of current was applied to the MRE device. This result shows that the MRE device can be used as a variable stiffness device for a controllable impact isolator. This result fall into an acceptable range to suggest that the device can be used as an impact isolator and damping device. This result also indicate that by using magnetic particle additive, it will provide a better result compared to non-magnetic particle additive because when the current is applied to the MRE device, the additive with magnetic particle will align to the current path like anisotropic configuration of MRE and thus improve the properties of the MRE. The next one is the fixed current with varied additive. So from here, ferrite has the highest force impact compared to the other additive because of its properties. The force can be compared from the starting point until 0.1 millisecond, which refers to the trend line. Ferrite, is the blue line, has the most significant force, followed by zinc, which is the red line, copper, yellow line, and lastly the aluminium, purple line. Pure iron is exceptionally soft, making it unsuitable for structural use. On the other hand, steel contains up to 2% carbon, making it the most frequently used engineering material. Carbon reinforces the microstructure of iron by filling the gap between iron particles, thus marking the ferrite's performance in this study. So the conclusion is the magnetorheological elastomer characteristics was determined using an impact test with various current supplied on different additives. It can be concluded that the value of forces increase when the applied current increase. Forces on magnetic additive are also higher compared to non-magnetic additive. Thus, this finding indicate that the MRE damping force can be adjusted by varying the current supply and used as a damping or isolated device in a real-world application. That's all from me. Thank you for listening.